What is up, Precalculus? This is section 8.2, which is talking about vectors in the coordinate plane. You already know what a vector is. It has a direction and a magnitude to it. And so a vector like this, if you put it in the coordinate plane, if it starts at the point x1, y1 and ends at the point x2, y2, then this horizontal distance it travels is going to be x2 minus x1. And the vertical distance it travels is y2 minus y1, so this length here. And so its component form, how much it moves left and right, how much it moves up and down, is just going to be the difference of those two coordinates. So for 1a, I don't even know if I'm going to do both of these. This in vector form is going to be 6 minus a minus 2. And then 1 minus a minus 7. So it's going to be 8, 8. It's going to be my answer. We can go into another one, it won't take long. So this is going to be negative 9 minus 0, so just negative 9. And then negative 3 minus a minus 8, so it's going to be negative 11. And there you've just written those in component form. The next thing we need to talk about is the magnitude, or just simply the length of a vector. So just think about the distance. So it's kind of the same idea that we were dealing with earlier. If we want the hypotenuse length, this is the horizontal distance, and this is the vertical distance. So we just take the sum of those and square root it will give us that third distance using the Pythagorean theorem or the distance formula, whichever you'd rather. So maybe let's go ahead and find how long each of these sides are, or essentially we're putting it in component form. So it's going to be 6 minus a minus 2, and then 1 minus a minus 7. So it's going to be that 8, 8. I think we just figured that out. So this length is 8, and that length is 8. So this hypotenuse length, which is going to be the magnitude denoted like this of the vector v, is going to be the square root of 8 squared plus 8 squared. Or it's just going to be 8 square roots of 2, which is approximately 11.3. Which brings us to our next thing, which is vector operations. So whenever they're already in component form like this, vector operations are pretty simple. So if we're talking about the addition, you just add the horizontal movement and then add the vertical movement to find the new one. Subtracting vectors, kind of same idea. You subtract the horizontal and then you subtract the vertical. And then if you're doing a scalar multiple, you just multiply that by the horizontal and multiply it by the vertical. So let's just try one of these, and I kind of put this close to the bottom. I'm just going to come over here to the right a little bit. So we have room. So 2w, w is that negative 4, 1. And then I'm going to say plus 4 times the y vector, which is 2, 5. And then I'm subtracting the z vector, which is negative 3, 0. Let's go ahead and simplify these down. So it's going to be negative 8, 2 plus 8, 20 minus, actually I can go ahead and say plus 3, 0, right? Because it's like a negative 1 distributed into those. So let's go ahead and add these two together. Negative 8 plus 8 would give me the 0. 2 plus 20 would give me the 22. I'm going to add to that this vector, 3, 0, which means it's going to be 3, 22. So this is what that comes out to be. All right, now a unit vector is just a vector that's 1 unit in length. And so if I have some vector, let's say it's this long, if I know its magnitude, right, how far it is from here to here, if I divide by its magnitude, then it's going to make it just 1 unit in length. Right? So it's kind of the unit vector is just the vector divided by its magnitude. So it's kind of helpful to define them, or we say it's a unit vector and going in the same direction, right? So the unit vector going in the same direction as this purple one would be this green one that's just 1 unit in length. And so in order to do that, we just need to find the magnitude of this vector. So let's find the magnitude of this x vector, which is just going to be the square root of the square of each of those. So -4 squared, because that's how far it moves left and right, plus -8 squared. It's going to be 1664, which is going to be the square root of 80, which is going to be 16 times 5. The square root of 16 is 4, so it's going to be 4 root 5. So then what we need to do is we need to multiply this. We're going to say 1 over the magnitude, 1 over this, which is going to be 4 root 5, times this vector, -4, -8. So that's going to give me -1 over the root 5, because the 4 and the 4 would reduce with each other. And then this is going to give me -2 over square root of 5. We know better than to leave those radicals in the denominator, so I multiply by the square root of 5 with the square root of 5, so it's going to be -√5 over 5, and -2√5 over 5. There we go. Now, the next thing we're going to talk about is some really important unit vectors. And these unit vectors, we name them I and J. And that's unit vector I. Notice it moves 1 in the horizontal direction, and none up and down, so it looks like this. And J moves none in the horizontal direction, but 1 in the vertical direction. So those are our unit vectors that just move horizontally or vertically. So if you take any vector, let's say this one, notice it has the component of 4, 4. I could rewrite this as 4 red ones plus 4 blue ones. Right, because if I added those together, it would get me to that same spot right there. So notice that would be the same thing as 4 red ones, which is the I, plus 4 of the blue ones, which is the J. So this is what we call a linear combination of unit vectors. Okay, and they're pretty simple to get. If you have it in component form, like let's just say it's 3, 2, then if you want to write it as a linear combination of those unit vectors, that would just be the same thing as 3I plus 2J. Really hard, right? I knew you'd say that. All right, so here are kind of the instructions. They'd say let DE be the vector with the given initial and terminal points. Write D as a linear combination of vectors I and J, so of these ones. So the first thing we want to do, something we were kind of already doing, we want to write this in component form. So 2 minus a minus 6 is going to be 8, and 5 minus 0 is going to be 5. Now that we have it in this form, it's really easy to write it in that component form, or a combination of those vectors. Sorry, now that's in component form, we can write it in a linear combination of the vectors. So it's going to be 8i plus 5j. Alright, so this brings us to something else that's super fun. If we have some vector that starts at the origin and ends at the point AB, we know that this length over here is going to be A, and this length here is going to be B. And we notice that it meets at a right angle. So let's go and just call this angle right here theta. So notice this red length, sorry, this is vector V. This red length is we could write this in terms of theta. So if I said cosine, which is adjacent over hypotenuse, cosine of theta would equal to the adjacent over the hypotenuse. Now the hypotenuse would be the magnitude of vector V. Technically I should put a little vector sign on that. Okay? And so then A would simply equal to the magnitude of the vector times cosine of theta. Likewise, if I use sine, sine of theta would equal to B over the magnitude of V. So that means B would equal to the magnitude of V times sine of theta. So if we want to write this in component form for that vector, would look like this. The magnitude of V times cosine of theta, and the magnitude of V times sine of theta, which is exactly what they ask us to do here in 3b. It says find the component form of V with the given magnitude and direction angle. So here we go. Since the magnitude of V is simply 24, this is going to be 24 times cosine of 210 degrees, and then 24 times sine of 210 degrees. Lucky for us, we have a unit circle right over here, 210. So this are going to be our two values. X is the cosine, y is the sine. So this is going to be 24 times the square root of 3 over 2. It's going to be 24 times, the negative, times the negative 1 over 2. So that is going to be what? Negative 12 root 3 and negative 12. Now let's say we wanted to go the other way. We wanted to somehow find that angle. Now if we know its component forms, if we know A and B, like we do here, we know tangent has a ratio of those opposite over the adjacent. So we can do something like this. I know tangent of the theta that we're looking for is going to equal to the blue, which is the negative 8, over the negative 3. Now just real quick, let's take a sketch of this. Negative 8, negative 3 is going to be over here. Right? So we're looking for this angle. So if we're looking for theta, we're going to take tangent inverse of 8 over 3. And we're going to just throw that in our calculator. And in our directions it says to the nearest tenth of a degree, so that theta is equal to 69.4 degrees. Now, if we know that this angle that we got here is 69.4, that actually just puts us up in this direction, right? And I actually kind of messed this up. This is actually -3, -8, so it'd be down here, right? So we're getting up here at this angle, so we're getting this one is being the 69 degrees, so we have to add 180 to that to find the actual one that I'm looking for. So I'm going to say plus 180, and then the answer I'm going to get is going to be 249.4 degrees. So that's the angle of that. Your homework today is a worksheet, so make sure you get that, complete that, and turn it in. You guys are going to do awesome.